In the last class, we saw how to figure out the quiescent operating points from the differential pair with active load. So here now we'll figure out the small signal equivalent circuit model for the entire differential pair with active load, because if you have more than one transistors, it's really difficult every time to come up with the small signal equivalent of each and every transistor. Rather, if you come up with the equivalent small signal equivalent for the whole differential pair with active load, it would be easy for us to proceed, and wherever needed we can directly use that model. So what I mean by that is, say let me first put down the differential pair with active load. So this is my VDD line, and I have my PMOS transistors that will form the current mirror. Okay, and then I have my NMOS transistors where I'll give my incremental signals. Right now, let me draw the whole picture anyway. This is V bias, and V bias the source node, and I'll have my tail current source. Okay, this is my tail node and this is my tail current source, and I0. I'll have a current of I0 by 2 here and I0 by 2 here. Okay, and we know how to estimate all the quiescent voltages. This is M1 and M2, M3 and M4, and we know M1 is identical to M2. Let's call their GM GM1, and M3 is identical to M4. Let's call their GM GM3. Okay, so these things are all GM1 and GM3 are all estimated at the operating point of I0 by 2. Right, so this much is clear to us now. Right, now let's see what is the small signal model of this entire differential pair. See, remember the output is taken here. I have taken the output here because I am going to apply plus VD here and minus VD here, and wherever I am applying minus VD, I know that node potential is going to increase, and that is convenient for me to take the output at. Okay, that is the reason. So I hope after the series of lectures on this differential pair, this should be very clear to you now. If not, I suggest you to watch these lectures again and again until the concept gets registered in your mind. Okay, now coming back to the implementation of the small signal equivalent of this whole network. Essentially, if you see, if I have, say for example, let me put it here, if I have a block, let me put everything in this block. Okay, if I have a black box, okay, inside which I have some transistors in some way connected or so. Okay, now incrementally, okay, these are all incremental pictures that I'm talking about. I have some transistors connected, and then incrementally I want to obtain some equivalent circuit. In that case, what I can do is I can short the output node to the ground and find out the Norton equivalent current IN. Okay, and this is equal to I out, right? Output current or the Norton equivalent current, short circuit current. This output node being shorted, for some value of V in. Okay, and this I out by V in is the GM. Okay, some trans conductance form. Okay, if you figure out that and if you multiply with R out, okay, then this factor will be gain of the transistor. R out is nothing but you take the output node. Okay, say the same black box that I am taking. Okay, the same black box, and this input should be deactivated. If it is a voltage input, it should be shorted, and then you look at it from the output side. Okay, then see what is R out. You figure out R out with respect to the ground. With respect to the ground, if you figure out what is R out and multiply it with GM, what you have figured out from here, then that is going to be your gain. Okay, so easily you can come up with the incremental equivalent. How many number of transistors are there inside, it doesn't matter. You can come up with an equivalent, incremental equivalent for this whole setup. Okay, what is there in the black box? Like this, you have some V in, and you have a current that is flowing into the output node. This output node is flowing into the output node. Okay, let's say this output node, multiply by this R out. Okay, remember this V in is with respect to the ground, and then, or V in is between these two terminals essentially. Say this is 0 volt, this is V in, so it's between these two terminals, and this is nothing but some GM times, or rather this GM times V in is this I out. Okay, multiplied by this R out is going to give you my V out, or the V out, and divided by V in is going to give me my gain. Okay, so GM times R out is going to give me my gain. Okay, so this will be the incremental equivalent of these two networks. These two are the same, so I can actually put down an incremental equivalent like this. Okay, it's very straightforward. You see, it doesn't matter how many number of transistors are there, I can come up with an incremental equivalent like this, and this will be exactly same as putting two inputs, and let's say see, I've denoted as V in alone one side, but it could be always V1 and V2. Okay, which is Vd and minus Vd. Okay, and this difference is going to be Vd, V1 minus V2, and then you put this is a Norton equivalent, so put a Thevenin equivalent for this, and I'll have a Thevenin equivalent in series with a resistor, and this is going to be R out, and this is appropriately GM V in times R out, right? So GM V in R out, and this will be your Thevenin equivalent, and this will be your V out. Okay, so you see, this is exactly the same equivalent as that of the opamp that we have started with. So essentially we are trying to realize an opamp, and this complete picture is an opamp in itself. Okay, but it's a single stage opamp, meaning it will not have a very large gain, but then it is sufficient. Okay, this is what we are trying to arrive at. Okay, we are trying to get an equivalent circuit like this from here. Okay, at least this one we can, if we can do it, then this is very, this is free from here. Okay, so let's try to do this this way, and your small signal equivalent for each of the transistors, how to put it, and then you try to figure it out. Okay, so let us do it here. I suggest you pause the video and do it parallelly and see if you are correct. Okay, so see, once you have done this and understood this completely, we will not be doing it again and again, because we are going to use this incremental equivalent, because eventually we will end up in this, and this can be used everywhere. Okay, so first let's start with getting the Norton current. So essentially what we should do is, you should ground this and try to find this current IN. Okay, so how do we do it? So replace all the transistors with this incremental equivalent. This will be open source, and this will be open circuited, essentially this current source. And remember, this node is not at 0, it is at some potential Vs, and then you have some gate at Vd, and this side also you have some gate at minus Vd, and you have your source current, or I mean gate source current. This is GM1 Vd minus Vs, but then if you see, Vs is the average of these two potentials, which is going to be 0. Here it turns out that it is 0, although it is not grounded, it turns out that it is 0. So that is why I am writing Gm times Vd. Otherwise it would be Gm times Vd minus Vs. Okay, so similarly here I have a current flowing like this, which is minus Gm1 times Vd. Okay, because minus is there, and Gm1, because these two transistors will have same Gm1. Okay, that's why I have written like this. Now from here I have the gate connected, I have the source connected like this, and this drain is going to the drain of other transistor, and this is diode connected transistor, where you have connection from the drain to the supply, which is obviously grounded. So you have a connection like this. This is also ground, this is also incremental ground, and you have 1 over Gm, because diode connected transistors will have a value 1 over Gm, and this is Gm3. Okay, and these two are shorted. These two are shorted, right? Now this portion of the drain is connected to the gate, okay, and that gate is being taken to the next transistor, okay. So this is, and what is this voltage? This voltage is negative of this current multiplied by this resistance, so it is going to be minus GM1 by GM3 times VD, okay, that is this voltage, okay. Now you have this gate voltage that is established, we have figured out what it is. Now the source terminal is incrementally grounded, right, and this PMOS equivalent is exactly same as that of NMOS equivalent. So from the drain to source you have another current that is determined by this gate voltage, okay. So you have a current from drain to source like this incrementally, and that is determined by GM VGS, okay, and source is grounded, VG is this one, and GM is GM3 times minus this voltage, okay, minus GM1 by GM3 into VD, okay, and this one and this one are grounded, connected, and here is where you have the output which is grounded again, and this current is a Norton current you want to figure out, okay. So you have three currents going out of this node, and you put the KCL at this node, you will get the answer, okay. So the three currents going out of this node will be equal to 0, so I can write it as minus GM3 times GM1 by GM3, okay, into VD minus GM1 times VD. I'm sorry, this is VD by 2, right? We said this is VD by 2 because VCM plus VD by 2 and VCM minus VD by 2. Okay, just make this correction. So everywhere it is VD by 2. It's also VD by 2, right? And these two currents in addition with this current IN will be equal to 0. So this is equal to minus IN. So IN Norton current is nothing but this is get cancelled, GMVD by 2 minus GMVD by 2 minus GMVD by 2 is minus IN. So GMVD by 2 plus GMVD by 2 is IN, which is GM1 VD, okay. Now this is with the small signal equivalent picture. I have received this particular current, this output current, this Norton current is GM1 VD that I have got, and VD is nothing but VD is nothing but V1 minus V2, okay, and V1 this is V2 side, and V1 we had VCM plus VD by 2, and V2 we had VCM minus VD by 2, and VCM is non-responsive, okay. As far as this circuit is concerned, VCM with this circuit will not respond to VCM. We have seen it multiple times. That's why we analyze only with VD by 2. So as far as the differential signals are concerned, this is the incremental picture, okay. Incremental picture will have this current source of value GM1 V1 minus V2, okay, or GM1 times VD, okay. This is what we wanted and we got it, okay. Now but for common mode the circuit is not responsive, but then we'll see what happens. But differential mode, as far as differential inputs are concerned, you can replace it with the current source of value GM1 times Vn minus V2, and you see it is pretty straightforward from here also, because we know that if this is VD by 2 and this is minus VD by 2, this node potential is anyway 0 incrementally. All the red markings are incremental signals. If this is 0, then this current is going to be GM, incremental current here is going to be GM VD by 2, and incremental current in this direction is GM VD by 2 because it is negative VD by 2, right? So this is a current mirror, okay. So whatever current that flows here, incremental current, that will also be mirrored here. So this GM VD by 2 will be mirrored here. So GM VD by 2 will be mirrored here, and GM VD by 2 is also flowing here. So this current, incremental current, is going to be GM VD. So GM VD by 2 plus GM VD by 2, I will get GM VD. That's exactly the same thing that I got it here, okay. So it's pretty straightforward, but then this is to give you a practice and you can always analyze it through intuition and inspection like this also. Okay, so Norton current that is flowing into the output node is GM VD, okay, into the output node, and you have an input side VD by 2 here and minus VD by 2 here. The difference is VD by 2 minus VD by 2 is going to be VD. Okay, so we just have to, half work is done. We just have to figure out what is the output resistance R out. Okay, this is something we have to figure out, and once we are done, our incremental equivalent is also done, and this figuring out R out we'll do it in the next class. Okay.